Hey, good morning, guys. My name's Chance Roberts. I'm a chemical engineer working currently as a process engineer at Pharmavite, a nutraceutical pharmaceutical company here in Opelika, Alabama. Currently seeking out my master's from Auburn University. I wanted to take some time today to present you some interesting information and research on conductive hydrogels, specifically in the application of high-performance strain sensors. When I think about the current state of strain sensors, the first thing that comes to mind to me is the wide use and popularity of these devices. They're used in a large number of fields, including tissue engineering, robotics, medical monitoring and medical devices, physical detection, just to name a couple. Our current model of strain sensor works based off of the coupling effect between mechanical deformation to electrical signal, normally detected by a change in conductivity of the material. Because of this, classical conductive materials have been used in strain sensor applications, which brings challenges, including the stiffness of these materials and the restricted stretchability of them. When it comes to sensors, that's particularly troublesome due to a couple of reasons, chiefly being the comfort. When used around high mobility areas such as joints, fingers, or other areas of the human body, that certainly comes into question their usability. Another question when it comes to these sensors is the adhesive measure used. One such concern would be immune responses due to these adhesive measures. Because of that, hydrogels as a strain sensor is an interesting option. Hydrogels bring with them the benefit of their tunability, whether by changes to physical or chemical bonding within the hydrogel, uses as additives or other materials to add properties that were not classically seen in hydrogels. Hydrogels really are one of the more tunable materials at our disposal. Uh, Things that we'd be interested in tuning in a possible strain sensor that could be accomplished through hydrogels would include conductivity through the introduction of conductive ions and other networks such as carbon nanotubes, adjusting the modulus through cross-linking, crystallization, or intramolecular forces. Another property that's not currently available to classical conductive materials would be self-healing and self-adhesion. These can be approached through the use of hydrogels. My group set out to see if we could feasibly come up with a novel compound that could combine and modulate all four of these properties into a potential strain sensor. In order to do that, we had to be strategic about the materials we pick. Starting with the carbon backbone, we sought to develop a complex matrix of intramolecular forces. The backbone, built from acrylic acid, will introduce a large number of carboxylic groups, which will contribute to carbon bonding. Chitosan was also introduced. This gives us amino groups to our compound, and we'll discuss this when we get to our ions. We'll introduce a complex ion coordination. T-phenols add the catechol group, or 1,2-dihydroxylbenzene. This plethora of OH groups gives us the capability to self-adhese to substrates due to these OH groups. It also has marginal benefits as an antioxidant and possible sterile agent. Ferric chloride hexahydrate was added to our polymer in order to induce free ions. This will elicit the conductivity of our ion, and also, as I mentioned before, will give us the ability to form coordination alongside our carboxylic groups and our amino groups. Lastly, to further modulate the modulus, carbon nanotubes were added to our mixture as well. Above me, you'll see a figure that kind of illustrates all of the different intramolecular forces that we have going on in our compound. Starting here to the left, we have an example of amino groups coordinating with the ferric ions. We have pi-pi stacking between a combination of two carbon nanotubes. We have coordination amongst the carboxylic group and amino groups, and we have coordination amongst just the carboxylic groups themselves. Adjacent to that, we also have the catechol groups. This large and wide breadth of intramolecular forces will come into handy when it comes to things like self-healing, where these interactions can bring two pieces of the polymer back together due to their strength. Now that we've decided upon the materials that we think will elicit the response, next came synthesis. This involved acrylic acid and chitosan and DI water at 50 C for 30 minutes, adding aqueous ferric chloride and T-phenols at room temperature, and most importantly, the ultrasonic dispersion of carbon nanotubes. As I discussed before, these guys have the pipi stacking, and they tend to agglomerate when not properly dispersed, so this step is extremely important. Last, the initiator was added and stirred for an hour, samples placed in an oven for 4 hours. For this particular research, we developed 4 different samples. What you'll notice is there is no modulation amongst any compound outside of the carbon nanotubes, with increasing weight percent from 0 to 0.20 weight percent. Now that we had synthesized our 5 compounds to be tested, we next needed to decide upon our physical testing to be done. The properties we would test, as I discussed briefly before, was adhesion, tensile, self-healing, conductivity, sensitivity, which combined with conductivity will give us our stress sensing. The first property we decided to test was the tensile properties. This was done using a universal material tester at room temperature. We took each sample from G0 to G4 and tested their stress strain at break, calculated their toughness and elastic modulus. What you'll notice here is that an increase in carbon nanotube weight percentage yielded an increase of toughness and elastic modulus up until the G2 sample. At this point, the physical cross-linking of the carbon nanotubes reaches a point that decreases the plasticity of the polymer and can be demonstrated in a reduction in the elastic modulus and toughness here in the G3 and G4 samples. Our largest toughness and elastic modulus can be noticed here on G1. The next properties to be tested were the adhesive properties. These properties were attributed to the hydrogen bonds and the hydroxyl groups present in the T-phenols. These properties were tested first with all 5 of the samples, G0 to G4, on a wood substrate. There was an applied load of 1 Newton for all samples, and you'll notice here that the adhesive strength increased with carbon nanotube weight percent from G0 to the G2 sample, after which there's a stark decrease from G3 to G4. We propose a similar mechanism to the tensile strength, where the cross-linking of the physical cross-linking of the carbon nanotubes contributes to the loss of the adhesive strength. We then took our G2 sample and compared it across a variety of different substrate surfaces. We found that wood and iron resulted in the largest adhesive strength, followed by glass, then PTFE. This shows us that topology of the substrate also plays a key factor in the adhesive force. Lastly, we were concerned about the adhesive strength over cycles, specifically as it regards to shelf life and reusability of these sensors. So the sensor was taken and debonded 5 subsequent times and rebonded, each time measuring the adhesive force. We found a retention of 99.5% of the adhesive force over 5 cycles. After completing the tensile and adhesive strength testing, we moved on to self-healing. This was done by taking a composite sample of each of our samples, slicing them in half, and then dyeing the samples and putting the samples back in physical contact, allowing the complex group of intramolecular forces to slowly recombine into the polymers. These were allowed to occur over 12 hours, and then we sampled a similar tensile stress to break for all of the samples listed here. we found that G2 had the greatest total break stress and strain after 12 hours. Therefore, we selected G2 to investigate over a 12-hour period. We found that the stress and strain at break increased over the 12-hour period from 4 hours to 12 hours. We calculated a stress healing efficiency based off of the ratio of the return stress and strain versus the original stress and strain, and found a healing efficiency of 90% for the stress and 95% for the strain. Lastly, we connected the samples to an LED to make sure that the conductivity had maintained itself through the self-healing. And as you can see illustrated by the illuminated light, it had maintained its conductivity through self-healing. That brings us to conductivity measuring itself. We first tested the conductivity across a 4-probe sample, 4-probe tester. We found that with increasing carbon nanotube content, conductivity increased. What you will notice is there appears to not be a critical carbon nanotube content like the elastic effects, so to speak. That being because the plasticity of the polymer did not contribute to the conductivity, only the free-flowing network of ions and their coordination with the carbon nanotubes, which explains why the conductivity increased with concentration and did not show a critical carbon nanotube content. With a known conductive polymer here, we decided to move on to resistivity testing and sensitivity. This was first done by calculating a relative resistance of the polymer and eliciting an amount of elongation to the different polymer samples, first at 100% strain. You can see here listed in A the different polymers at different strain at 100% strain and the comparison of their relative resistance. You'll see that with increasing carbon nanotube concentration and therefore increasing conductivity, as mentioned before, the relative resistance increases at 100% strain from G0 to G4, with no, as I mentioned earlier, no critical carbon nanotube percentage showing itself. This was also done with the gauge factor, which is essentially a comparison of the relative resistance divided by the elongation ratio, which is a standard for hydrogel polymers to look at the conductivity with the effective strain. And you'll see a linear relationship here, yet again, with the increasing of the carbon nanotube percentage. We took a sample listed below from G2 yet again, and we then elicited different amounts of strain and compared the relative resistance change with the amount of strain, and found that with increasing strain, we had an increasing relative resistance from 100 to 600%. And yet again, a linear relationship with the gauge factor versus the strain percent. Now that we had isolated both a conductive and sensitive polymer, we moved on to finding a real-life application, which involved application of the hydrogel to an individual. These were placed on 7 different locations: on the throat, on the elbow, on the fingers, on the wrist, and on the knees. The subject then elicited deformation by actuation of these various points. The throat by saying the phrase "ah" and swallowing, the fingers by extension, the wrist by curling, and the elbow and knee by curling as well. What you'll see is as the polymers deformed via the actuation, we elicit a change in the relative resistance. You can see also that the return and response of this appears to be pretty quick, allowing rapid readings of the change in resistance. In conclusion, we were able to show that it is possible to design a hydrogel with with our different properties that we were looking for. Notably, we were also able to modulate these different properties via the carbon nanotube weight percent. We increased the elastic modulus, toughness, adhesion, and healing efficiency with an increase of the carbon nanotube weight percent. Interestingly enough, these four properties illustrated a critical carbon nanotube weight percent, which was found at weight percents larger than 0.1%. We also illustrated that an increase in carbon nanotube weight percent increased the conductivity, sensitivity, and the gauge factor, and did not show a critical weight percent. We then were able to illustrate that these samples could be used as sensors and were capable of detecting both small and large deformations, such as bending of joints and speaking. Looking back on our work, I had a couple of concerns with the paper. Specifically, it didn't mention what weight percent was used for the human motion testing. I guess keeping consistent with the rest of the paper, I assumed it was the G2 sample, but looking at how the conductivity changed drastically with the carbon nanotube weight percent, it'd be really nice to understand what exact sample we were working with. Secondly, alongside the human motion testing, there were a lot of unclear, undefined variables, such as frequency of the bending, angles of the fingers, wrist, and knee, not explicitly stated. Therefore, the deformation is kind of left unknown. Lastly, one thing I'm kind of unfamiliar with in papers about polymers is no real consideration to the thermal history or the crystallization of the polymer itself. I would have liked to have seen a discussion about the DSC of the polymer, but that was not provided at all. Things I think could have helped the paper. Moving forward, I think there's a lot of interesting and unanswered questions as well. When you're dealing with a hydrogel, you always have to take into consideration temperature and humidity, especially with something like this that has so many carboxylic groups and alcohol groups. This is something I'd expect to be extremely hydrophilic. So I would be very curious about the effects of temperature and humidity on this hydrogel, specifically the function of water acting as a plasticizer, something that I'm very familiar with work. Next, I would like to see, moving forward, kind of a modulation of our non-carbon nanotube components and seeing how they affected our properties. Currently, as it sits, the only thing that was changed was the carbon nanotube weight percent. Here's our references and our acknowledgments. And I've had a great time presenting to you guys today. I hope you guys learned something. I know there's a lot of information, so feel free to reach out with any questions either at my work email or my school email. Thank you guys.